Good morning everyone, hope you all safe with the good health. With you Ms. Dina Al-Badri, a science teacher for grade 8. Today we will complete our lesson properties of the waves. We talked last time about the wavelengths, period and frequency. Today we will talk about what affects the energy of the wave. As a wave moves through a medium, particles may move in a different directions or come to rest in a different. As the wave travels through more of the medium, more energy is lost to the medium. So we say that when the wave carry more energy, it means it has high frequency, have high wavelengths, and have high amplitude. High frequency wave lose energy more readily than lower frequency. Okay, more rapid than low frequency. Okay. Many waves spread out in a circle or spheres called wave fronts. As the circle expands, there is less energy available on the wave front. So, what is the wave speed? Or the speed at which wave travel? Depend on the properties of the medium. Waves tend to travel more slowly in a denser medium. Okay, so the wave can't move very fast when the medium is dense. In gases, wave speed is higher at high temperature. All electromagnetic waves travel at the same speed in empty spaces, but they travel more slowly through a denser medium. So when the medium contains more particles, so the speed of the wave decreases. So in the space, the speed of the wave it will be larger than in any other material, so even gas, water, or solid. Wave speed can be calculated from the frequency and wavelengths. So there is a relation between speed, frequency, and wavelengths. Speed is the distance divided by time. The speed of the wave equals its wavelength divided the period. So in general, the speed equals distance divided time. But the speed of the wave distance is the wavelength. In the time we called it period. Okay, so the speed of the wave equal wavelength divided period. This relation can be combined with the relation between wavelength and frequency. Wavelength is equal to wave speed divided by frequency. Okay. In this video, you are going to know what is the relation between the speed, wavelength, and frequency. That's all. Hope you all understand. Please check your LMS and print the sheet.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 107. It's on wave speed. If you spend any time in a thunderstorm, you know that the light reaches you much quicker than the sound does. And so if it's far away, there will be a big gap in those two waves' arrival time. But as it gets closer and closer and closer, the time between those two waves arriving, the light, and then the thunder is going to get closer and closer and closer. That was pretty close. And so waves transfer energy through oscillations. Since we're talking about wave speed, what is a speed, remember? It's a distance we travel over a given period of time. Now, how do we measure distance when it comes to waves? That's going to be the wavelength, or lambda. How do we measure time when it comes to waves? That's going to be the period. So if we simply divide the wavelength by the period, we've now calculated the wave speed. Now, the wave speed is going to depend on the medium. In other words, what it's in. For example, sound's going to go much faster in water than it does in air. So the medium determines that. But there's an established relationship between the velocity of the wave and then the lambda divided by time, or the lambda divided by the period. Now, lots of times, since the frequency is the reciprocal of the period of time, and so instead of being written like that, it'll be written like this: V equals lambda f. In other words, the velocity or the speed of the wave is the lambda, or the wavelength, times the frequency. And so let's take a look at that wave speed for a second. And so we'll just do this qualitatively. So what I'm going to do is start some waves in this simulation, and then I'm going to play around with the tension. And watch what happens as I make it less tense and then more tense. I could also affect how much of it is being dampened by the medium itself. And so you can see that I can play around with the medium itself and I can vary the speed of the waves. So let's just look at one for a second. So we're going to keep that tension the same, but we're sending one wave down and we'll stop it right when it gets to 6 centimeters. And so now we've watched the wave move. So we're going to try to calculate wave speed in a couple of different ways. So it's moved a set distance from here to here. And again, I had the clock running, so it took 1.6 seconds for it to make it there. And so if I want to figure out its wave speed, one way to do it was simply measure distance divided by time. So what's the distance? In this case, we moved 0.060 meters per 1.6 seconds. You can see I converted that to meters. And so what's going to be the wave speed just watching the wave go? It's going to be around 0.038 meters per second. Now we also know that you could calculate it in a different way. And so velocity equals lambda times frequency. And so we could calculate lambda. Lambda is going to be the wavelength. So let's figure out what the wavelength is. So from here to here, it's 1 to like 2.5 centimeters. And also on the simulation, it's telling us what the frequency is. And so if I know the frequency and I know the wavelength, I know the velocity. And let's make sure that that matches. So my wavelength is 0.025 meters. My frequency is 1.5 hertz. And so it's going to be 0.038 meters per second. So same thing. We could then try to change the makeup of the material or the matter through which the wave is moving. So let's start it now. So we've increased tension. So it went faster. You can see the time is less, so it's 0.96 seconds. So we could calculate the distance we moved. Again, that's 0.060 meters per 0.96 seconds. So that's one way. So we could get a velocity that's fast. It's much faster than it was before. So as we increase tension, we've increased the speed. But we could also use V equals lambda F. And so what is our lambda? What's our wavelength? It's going to be that distance. And what's our frequency? 1.5. And so we could say it's going to be the same value. And so those are two ways we could calculate the speed of the wave. Now what happens if we totally decrease the tension? There's no tension inside there. Oh, you can see that it's going really, really slow. And so I'm not going to keep going on this one. It'd take forever. And so as we increase the tension inside the material, you can see we're increasing the speed. So here's some speed of sound. So this is in air, 331 meters per second. In water, it's much faster. And in steel, if you were to just hit steel and then listen to it really far down, it's going to go way faster than it would inside the air itself. Now let's say we keep the medium the same. Let's say we keep the tension and everything the same. What's going to be the relationship between the wavelength and the frequency of the wave? And so let's just start it going. And what I'm going to do is vary the frequency. And so as I increase frequency, what happens to the wavelength? You can see it decreases. As I now decrease frequency, what's happening to the wavelength? Now you can see the wavelength is increasing. So again, the medium determines the speed of the wave, but then there's this relationship between the wavelength and the frequency. Lots of times you'll be given problems like this. So for example, we're given this picture. You can see the distance between the waves is 23 meters. We know the velocity of the waves is 2.8 meters per second. So could you calculate the wave frequency? So here's my equation. So V equals lambda F. I plug in what I know. In this case, I know the velocity and I know the wavelength, and I could solve for a frequency of 0.12 hertz. Or you could try this problem. Now I'm giving you the period. Let's say it's 3.5 seconds you're watching it, and that's how much time it takes for the boat to move up and down. And you could also measure the wavelength. And so could you calculate wave speed? Well, give it a try, and then include your answer in the video descriptions down below. And so did you learn to design an experiment to determine the relationship between the wave speed, the wavelength, the frequency, and relate those to everyday examples like lightning? I hope so, and I hope that was helpful.